Okay, so we're going to get started. My name is Laura Carriere, and I work at the NASA Center for Climate Simulation. And I'm here today to talk to you about a web-based visualization tool called CreateV, which uses, right here I get a lot of feedback. So I'm going to stand on this side. It uses climate models that have been that have observational data inserted into them as well from 1980 through the present. And this allows us to investigate extreme weather events that have occurred in the past. So I'm going to start by talking about atmospheric rivers. And just for those of you who don't know, an atmospheric river is a weather phenomena that channels water vapor through the atmosphere in a fairly thin line. When these occur between Hawaii and the U.S. West Coast, they're often referred to as the Pineapple Express. And while these events can be fairly destructive in the amount of rainfall they bring, they also bring the majority of precipitation to California, so they are very important. So, how would you find an atmospheric river if you didn't know when one had occurred? We, at the NCCS, have recently released a server-side analytics tool which allows people to, from their home computer, without having an account at NASA, use NASA resources with a set of predetermined commands and NASA data without having to download that data. So all you need is the client software, which you download to your own system, and a little bit of Python. So this Jupyter notebook right here, you can see that we are selecting the San Francisco, the dates from 2014 through 2017, and we are selecting MERA 2 monthly precipitation data, and we are going to do a maximum. So we run the command, it takes just a few seconds to complete, and we have a nice little plot here where we can see in January of 2017, that looks kind of interesting. So we can rerun this code very simply by changing this to 6-hourly data and just looking at January 2017. At that point, we get this plot over here where we can see that January 8th is even more interesting. So now let's go to the CreateV tool, which is shown here. And from here, I can select my reanalysis, my collection, this is MERA 2 data. The variable is precipitation. I've picked the January 8th for the date and 6-hourly data. You click Submit at the bottom, and you zoom in, and you can see that, yes, the atmospheric river is dumping a lot of rain on San Francisco. You can use the pushpin to actually see that that point in time was about 300, just over 300 millimeters per day. You can also use the color bar. You can modify the maximum and minimum to bring out additional features in your data. So we have multiple reanalyses. So I had my staff put together a couple of movies for January, so we can see all of January. And we're going to look at MERA 2, the European ERA interim, NOAA CFSR, and Japanese JRA 55. So here we have them all side by side, and what's interesting about this is the MERA 2, ERA interim, CFSR, and JRA 55. Is you can see similarities, but you can also see differences. And the usefulness of this is to allow scientists to see where their models agree and perhaps are doing well, and where they disagree and might need some improvement. So that was January of 2017, and for anyone who lives in California, you know how wet you got. So a couple of other extreme events we're going to look at. This is a heat wave, looking specifically at August 2003. And again, you can use the pushpin, and what this does is also run some analytics. This is some software, it's a precursor to the analytics software I talked about earlier, and all it does is calculate an anomaly and a yearly cycle, but we're going to hook it up to the rest of the analytics when we get a chance. You can mouse over on the tool itself and see what you've got in terms of, here's August 2003, and that is definitely a peak. You can also see a peak over here, but that was winter. This particular heat wave caused a lot of crop failures and about 15,000 deaths in France alone. So we want to study these things to understand the impact on humans. Over here we have Hurricane Sandy, and this shows our ability to do a compare feature. And we have looked at air temperature at 80 kilopascals on October 29th, and again, that's 6-hourly data. So we have also other variables that you can use. You can look at through here, like precipitation, east winds, north winds, geopotential height. I'll show you the list at the end. So we like this tool so much, we decided to add the global modeling and assimilation aerosol forecast data. This is a layered product where green is carbons that are usually caused by forest fires. White is sulfates, which comes from industrial. The red is dust that has been picked off the Sahara Desert. And then we have the light blue is sea salt. The interesting thing about the sea salt is it gets picked up and you can actually see hurricanes. So on the next slide, we have Hurricane Harvey coming up and hitting the coast. But of course, once it hits the coast, which is where most of the precipitation occurred, you can't see the sea salt anymore. So we have also looked at Irma, which you can see coming right up through Florida, and after that one, and then dissipates over land. And then the last movie is Hurricane Maria, which gets quite large, devastates Puerto Rico, and then heads off. Now, I do want to point out that this is a forecast, so Hurricane Maria did not reform in the North Atlantic, but it does, again, allow scientists to determine whether or not their code is working well. In conclusion, I have the list of other variables that we have. We also have ocean data, but I was unable to, I don't have enough time because she's waving at me in the back. And we have 8 ocean reanalyses, an ensemble mean, standard deviation. There's some temperature, and those are the actual variables. I want to say thanks to the folks in the corner. Without them, this code would not exist. And thanks to all of you for your time.